koutou. Thank you for that introduction. So just so that people can place me, since you already know where I'm from, I'm also a Thatcher from Tolaga Bay. I'm an O'Brien from Te Kaha, and I am a Blewett from Whakatane. Kia ora. So for my PhD, my project was undertaken, like you said, through Tiwai Ora, but I focus on essentially cleaning wastewater using slime, okay? That's what I do. So I don't want to talk too much today about the issues in our freshwater environment because we've all had those bad stories and we know how bad it is. But I did want to use this picture just to demonstrate an algal bloom that occurs. This is the Selwyn River in Canterbury, and between these trees is an algal bloom, okay? So when the nutrients is high, the nitrogen and phosphorus, algae appears. And that's because nature's just trying to compensate, right? Because I believe it self-regulates. So my work is simply a replication of what nature already does, except I do it in a more refined manner and I do it contained to treat our wastewater. But thinking about the kaupapa of this conference, I was thinking about my own tupuna. And my uncle once told me a story about my whānau many generations ago when they used to go and have their battles and their wars, and they would come back all beat up and they would have their wounds, and they would head to the Motu River along the East Cape. And there is a waterfall, and along that waterfall they would line up and they would put the men who were weaker on their shoulders, and they would line up in a row and they would stack each other up and they would lean back into the waterfall. And why was that? Because there was algae growing along the rock face of the waterfall, so they would allow the algae to wash over their bodies and they would stay there for days because they understood that algae was healing. And so my whānau have always known that. And I connected it back to water. So my tupuna used to use water to heal themselves, and now I use that. They used to use the algae to heal themselves, and now I use algae to heal our wai, in hopes that it will heal our people. So when people ask me, what do you do? I say I clean water, but that's not actually the case. The algae cleans the water. What I do is I facilitate the space, and I'm the kaitiaki, to allow the algae to do what it needs to do. And I'm also the storyteller. So I tell the story of what the algae does and how it heals the water. So my PhD project, it was quite unique because it focused on primary wastewater. So typically overseas, when you would hear about algae treating wastewater and taking out nutrients, it would be at the end of a wastewater treatment plant, so you would use it like a wetland. But my project is to use it at the start, with greater aspirations to remove wastewater treatment plants altogether for rural communities and replace them with algae systems. So it's a real natural way to be able to clean water. This high-rate algal pond was actually set up in Canterbury. One of my supervisors, Dr. Rupert Craze at Niwa, had used this just simple pond system, but he used microalgae. So unfortunately, a lot of the studies had been focused on microalgae, but the reason why it doesn't work is because it's hard to separate out that algae from the water, right? Because it's like green juice. So I use the bigger stuff. I don't deal with microalgae, I deal with macro. Okay, so there's like seaweed, you just harvest it out. Yeah. So just so for context, that's what I'm talking about. So there's two ways that it cleans the water. It's through, it assimilates the nutrients, so it takes up the nitrogen and phosphorus and turns it into biomass. And then it also, depending on the species, will host a particular type of bacteria that will speed up that process. Okay, so what I'm going to do today is I'm going to tell you the story of how to clean water so that you can clean water in your own land, okay? So it's real easy, and it's cheap, and it's simple, and it's natural. So what you're going to do is you're going to dig a hole. You want it to be in this shape, okay? And then what happens is that you want it to be in the shape of this. You just need to put a wall in, and then you install a paddle wheel so that the water goes round and round. But it's not to move the water as such, it's actually to keep the algae in suspension. Because what you're going to do is you're going to fill up the pond with your wastewater, and then you're going to chuck in the algae. And just to keep the algae vertical in the water column, because it's a bit of depth. Also, too, primary wastewater, it ain't clear. So that's what the paddle wheel's for, but you run the paddle wheel, with a solar panel. Okay, that's what they do in South Australia. It doesn't need to cost you anything. So this is the Coastal Marine Field Station. I'm not sure how to get there. So this is actually where I'm based, in Tauranga, and we have the macroalgal aquaculture research facility. There we grow up freshwater algae, and we also do seaweed research. They're just small high-rate algal ponds like I'm talking about, and they run on freshwater and saltwater. And we actually clean all the water on site, so it's just reticulated round and round. So that's how I can grow up enough biomass so I can take it out to the wastewater treatment plant, because my colleagues aren't too keen on me bringing in heaps of wastewater, So, yeah. If they smell poo, they know I'm around. Straight up. They're like, did you clean your gumboots, oi? Yeah, and wait till later when I have to heat it up, And they're like, do you have to heat up the poo? I'm like, oh, well, you'll get used to it. So just to talk about the genus, so like just when you're out in nature, you see green slime, right? Actually, if under the microscope, they all look very different. Okay, but we only identify them at genus level, because once they get to species, they start to look the same. I can kind of tell them apart, but I mean, there's plenty of hours, with Netflix on, just trying to study these things. But also too, as they grow, they change the way they look under the microscope. So they say there's thousands, but there might only be 10. They change the way they look as they age. There's 3 different types of cultures that you can have. You can have a monoculture, a biculture, a polyculture. You need a monoculture. The reason being is because different species like to clean the water at a different rate. Okay, so the fundamentals of making this system and implementing it into society, the main thing that you need a good species. So I've developed a protocol to be able to select the species. And you can actually apply this to any type of waterway. It doesn't have to be primary wastewater. If you've got a polluted lake or a stream or a river, you can just follow this protocol and tailor it to your specific needs. So the screening protocol, there's a few things that the species needs to be. It needs to be local for biosecurity reasons. Also, too, you hope that it's adapted to the local climatic conditions. Also, that it has seasonal performance, because you want it to be able to perform all year round and be able to clean the water. It needs to remain competitively dominant. Reason being is because you can get other algae entering into the system, because it's just an open pond system. And you want it to be highly tolerant, because the stuff that's coming into their wastewater treatment plant, most people think, you're just dealing with feces and urine, but I tell you what, most of it is actually your washing machine, your dishwasher. So sometimes I turn up there and it smells like frangipani. Straight up, frangipani. Oh, and also too, we've got to stop eating corn. It's just as yellow and whole at the wastewater treatment plant as it is on your plate. Straight up, every morning I have to go out there and filter it out. And I told them, I was like, if you guys don't stop eating corn, I'm going to can it back up and sell it back to you to pay for my research. Far out. You should have heard the Downer boys come, They were like, that's disgusting. I can see my dinner from last night. And I was like, oh, bro, do this every day. Come on. So first thing you're going to do, quick, because we've got 6 minutes. The first thing you're going to do is sample collection. So as I said, you just go out to your local area. So I was targeting the Te Puke wastewater treatment plant. So you can actually get most of the algae in the wastewater treatment plant. I just told the guys not to clean it. And it grows along the walls in the UV section. It grows all around. But I also went everywhere because I was like doing my PhD and I wanted to be, thorough. So I went to the river, to the Kaituna, the outlet for the wastewater treatment plant. But my winning species I found on a ditch on the side of the road, so you just never know where you're going to find it, Once I got all my samples, so that they only need to be small, I took them back into the lab, and then for 28 days I acclimate it. And what I do is I dose it with really high ammonia, and the reason being is because in primary wastewater, nitrogen is mainly in the form of ammonia, okay? And that's because mostly because of urine. So what can happen is you get spikes at the wastewater treatment plant. For instance, everyone has their morning coffee, so there'll be a spike later on in the afternoon because, you'll drink your coffee. And then on the weekends too, at night, Friday, Saturday, because you were drinking. And then for Nelson, it was last night, Yeah, so you gotta make sure that the algae can actually handle it, because for some algae, the ammonia is toxic, right? So it's kind of like Survivor, you gotta kill them off. So I want the best one. So after 28 days by natural selection, you should have a dominant one. And then this is when Netflix comes on. I actually was able, you have to isolate them out one by one with your little tweezers, and then you just grow them up. So they double or triple in biomass every week. So you get into a bucket, 1,000-litre tank, so on and so forth. And then what I did is I put it through seasonal effects. So what I was trying to establish is whether or not they'll be able to grow throughout the seasons. Okay, so I mimicked Te Puke's summertime, wintertime. I even put them through extreme conditions, heat wave, frost, 1 degree. I was like trying to kill them. And then I was trying to see whether or not they would still clean the water under those conditions. And if you see this little picture here, that's the clarity that I can get in 24 hours, okay? Yeah, so that's because the bacteria and the algae are working together. I did actually do it just with just with wastewater to see what would happen, and it wasn't as good as the algae. So these are my results. If you just look here, these are the concentrations. Now, to be honest, I actually diluted it today because I didn't know if it was going to work when I did my experiments, because I was a bit nervous. So I diluted the wastewater so these concentrations aren't too high, but this was at the start and this is at the end, okay? So these ones over here, they're a bit lazy because they didn't really clean the water under the extreme winter conditions. But there's one little here, and what happens is even if there's a little bit of residual nutrients left over, that's fine. It just means it needs to be left in contact with the algae for longer. Okay, that's all that means. The only thing you got to watch out for, though, is that sometimes it looks like it's cleaning the ammonia, but it's actually just becomes nitrate. So you just got to watch out for that. So I test for both just to make sure I'm actually taking out the nutrients. And then the final step is, once I've chosen my best species, I grew it up at the field station, I took it out to Te Puke, and I put it through these little mini high-rate algal pond systems before it's goes into full implementation. And I was managed to be able to clean the water in 4 days. I got the ammonia concentrations down from really, really high, even up to 50 milligrams per litre, and I think it might have had something to do with the kiwi fruit season was on at the time. But I was able to get down to 0. It's not on the graph, but I did the calculations. I can get it down to 0, in 4 days. But hopefully this summer I can get it down to 0 in two or 3. Because in summer you have, usually you would have a better result. Yeah. Okay, so other things that macroalgae can actually take out of the water, and this is of real interest to me. So if you've got things like aluminium or something in your water, algae can definitely help you with that, okay? Because it takes up heavy metals, we already know that. It also reduces pathogens, but that's more to do with the system itself. And microplastics, so this was something you didn't really think about, but everyone does their washing, right? And you've got lots of microfibers ending up at the wastewater treatment plant. And what happens is the algae wraps themselves around all those microfibers, and it actually, we take out tons and tons of microplastics out of the wastewater, okay, to go with the algae. Also emerging contaminants, so this one's important and I don't think it's spoken about enough, and I'm not too sure if people are aware, but for instance, this morning some of you would have had to take an ibuprofen or a Panadol, right? Well, what actually happens is you urinate most of it out, it ends up at the wastewater treatment plant. Wastewater treatment plants aren't designed to treat those types of pharmaceuticals, okay? They end up in your stream. But what I'm concerned about is when you get ibuprofen, mixed in with an antidepressant, mixed with your antibiotics and methamphetamine, and there's a cocktail, and what does that mean for our ecosystem? We don't know, okay? And that's a real concern to me. And so one thing that I have been working on, though, is a particular type of forever chemical. And I want to thank you very much for supporting me for my research, because this type of chemical, it's everywhere, okay? It's called per or polyfluoroalkyl substances. It's in your carpets. If you've had to wear a waterproof jacket today, it's on that. It's on your phones. Okay, it's everywhere because it's a class of chemicals that makes things water resistant, heat resistant, and stain resistant. Okay? It's now found in soil, groundwater, drinking water. It bioaccumulates in animals, and it's in all of you. Okay, but the thing is that it causes all these health issues. Okay, so there's all sorts of different types of chemicals and all these things that can happen because it's bioaccumulating within us. We don't know how to get it out of wastewater worldwide. And so I wanted to try. Because sometimes when a problem seems really complicated and overwhelming, the solution is actually really simple, hey? And nature can heal. So I don't actually have my results yet because I just finished the experiment before I got here. So I'll find out in a week or two. But also too, just to finish off, one thing to consider, and that we are working on as well, is that once you clean the water with the algae, right, it grows and you have to harvest it out. So what are you going to do with the algae? Because the algae is then toxic, okay? So you don't want to put it into landfill because it'll just end up somehow back into the ecosystem. You can't have it for human consumption, animal consumption. That's not an option. One of the best options I've come across is making it into toilet paper because then it just goes back into the system. Biofuel would also be good, but I am slightly working on product application and what happens to the chemicals, in that when you're actually making it into a product. Okay, that's it. Kia ora, thank you. Thank you.